Hello and welcome to my video How Shadows Debunk Flat Earth Part 2. Last time we talked about how shadows in locations south of the equator debunk flat Earth. This video is about an experiment you can do anywhere on flat Earth. It's so simple, literally all you need is a pointy stick, a watch and sunlight. No calculator, no instruments, no telescopes, no formulas. You don't even need to see the horizon. You can conduct this experiment right in the middle of a city. Sadly, it's currently winter in the inner part of our flat Earth, and as you need a few hours of sunlight for this, I intend to conduct this experiment myself at a later point. But you are welcome to conduct it yourself and to upload your video about it. What determines the location of an object's shadow? It's a geometric transformation called point inversion, sometimes also referred to as central inversion or point reflection. A point or group of points is reflected through an inversion center to its opposite side. In 2D, inversion is equal to a rotation by 180 degrees. The most important part is that inversion is a so-called affine transformation. That means that distances stay the same, angles stay the same, proportions stay the same. A pyramid stays a pyramid, a square stays a square, a circle stays a circle. Now, let's apply this. Here we have a light source changing location over time. It's at one location at t equals 1 and at another location at t equals 2. We use the object casting the shadow as the inversion center, and this gives the inverted location of the light source at t equals 1 and the inverted location of the light source at t equals 2. Now we add a plane onto which the shadows are projected. We project the inverted image onto the plane while accounting for shrinkage due to perspective. And this gives us the locations of the shadows. And this works no matter how the plane is tilted with respect to the light source, be it this, or this. Now, lucky for us, the flat Earth model is very simple, and it's very simple to deduce what shadows on a flat Earth would look like. According to the flat Earth model, the Sun moves at a certain altitude above flat Earth in a circle in a plane that is parallel to the plane of flat Earth. Changes in radius are irrelevant because they happen so slowly over the course of a year. If we consider a time span of just a few hours, then for any and all practical purposes, the Sun moves in a trajectory that is a circle segment. So what are the consequences of this? Inside view. The Sun moves in a line that is parallel to the surface of flat Earth. That means the inverted trajectory of the Sun is parallel to flat Earth, and that means that the trajectory of the shadow on the ground is parallel to flat Earth. And that means that, except for a scaling factor due to size change, the trajectory of the shadow on the ground is affine to the trajectory of the Sun. Let's look at the situation in top view. We have the trajectory of the Sun, the inverted trajectory, and the projection of the inverted trajectory. Again, because the Sun moves in a plane that is parallel to the plane of flat Earth, a circle is transformed into another circle, is transformed into a smaller circle. And here we have the same situation viewed at an angle. We have the Sun moving in the sky in a circle. We have a vertical stick sticking out of the plane of flat Earth. Using the tip of the stick as the inversion center, we determine the inverted trajectory of the Sun. And then we project the inverted trajectory into the plane of flat Earth while accounting for shrinkage due to perspective. And this is the result. If the Sun moves in the sky in a circle, then the shadow of the tip of the stick must move on the ground in a circle. Now, if we tried to conduct the experiment like this, we would run into two problems. First, we would need 24 hours of sunlight. Second, we would need to quantify mathematically whether the roundish course of the shadow is indeed a circle. But don't worry, geometry is here to save us. Inversion is an affine transformation. Angles stay the same, proportions stay the same. A pyramid stays a pyramid, a square stays a square, and a circle stays a circle. And a quarter circle stays a quarter circle. This sketch here shows how the sun would move from 9 AM to 3 PM, 90 degrees, a quarter circle, over the course of 6 hours. And because of all the geometry we have talked about, if the sun moves in a quarter circle, then the shadow must move in a quarter circle, no matter when you start marking positions on the ground. And it's very easy to measure whether the curved line on the ground is a quarter circle. All you need is measuring whether its ends are at 90 degrees to each other. In summary, the flat Earth model claims that the shadow of the tip of a vertical stick moves on the ground in the geometric shape of a quarter circle over the course of 6 hours. Not the direction of the shadow of the stick, but the trajectory of the shadow of the tip on the ground. If we observe the moving of the shadow and it moves in a quarter circle, then this is one piece of evidence supporting flat Earth. If it moves in any other way than a quarter circle, then flat Earth has been debunked. As I said in the beginning, it's currently winter in the inner part of flat Earth and the sky is cloudy most of the time in Europe, so I can't conduct this experiment right now. But I would be more than happy if someone else with access to sunshine would take the time to conduct this experiment and post their own video about it. All you need is sunshine, a watch, and a stick that doesn't even have to be perfectly vertical, so long as its tip is its highest point. Thank you for watching my video, and please go check out these channels. Goodbye.